Okay, so now moving on from combinational logic to sequential logic. So sequential logic introduces a clock. Okay, and the clock is used to sequence your logic. And that'll become clearer as we talk about it. So let me first introduce a D flip-flop. Often we just refer to this as a flip-flop. There are other flavors of flip-flop. D is the simplest, and other flavors of flip-flop essentially just incorporate logic functions into the D flip-flop. So we will talk only about D flip-flops and just refer to them as flip-flops. So a flip-flop is responsible for allowing values to propagate. So the D flip-flop itself holds on to a value. So the flip-flop here is holding on to, we can assume this is just a single state, a single bit of state. So this D flip-flop is holding on to either a 1 or a 0. And when the clock edge comes along, so in this case the rising edge of the clock, we will allow the next state, which is either a 1 or a 0, to propagate through to the state. And the flip-flop will hold on to that value until the next clock edge. And we'll see how we use this D flip-flop. But essentially, logic with flip-flops is sequential logic. So a sequential circuit, because it is holding on to state, needs a way to get the circuit into a known state. This is like booting your laptop or resetting your laptop. And we use a reset signal to do that. So the reset signal is asserted for generally a long time. And the reset signal is used to get all of your flip-flops and all of your logic into a known state. So many of the flip-flops, if not all of the flip-flops in your circuit, will also have a reset input. And on reset, the state will go to either a 1 or a 0. And then after reset, your circuit is allowed to continue on and do its thing. We can view your sequential circuit in its entirety as a big state machine. Okay, so the combinational logic that we looked at before, where you have some set of input bits, and based on the combinational logic, those input bits propagate through logic gates and very quickly result in output bits. Now those output bits we can look at as our next state values. And with every cycle of the clock, our state goes through combinational logic, resulting in next state, and with each clock edge, we allow that next state to become our state. So with each cycle of the clock, we're performing some new computation in our combinational logic, and we just iterate on that. Every cycle, we repeat that computation based on our updated state. So that should give you some general context for how we control time in a sequential circuit. We'll now go through some examples, and it'll start to become clear how we utilize sequential logic and build sequential circuits that do meaningful, useful things. So the first circuit that we're going to look at is a circuit that's computing the Fibonacci series. So the Fibonacci series is a simple series that starts off with two 1 values, and each next value is the sum of the previous 2 values. So 1 plus 1 equals 2. 1 plus 1. Yeah, 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8, and so on. So this is a circuit that will compute the Fibonacci series. So if our circuit is currently holding on to a value of 3 and 2 in the flip-flops, and then the rising edge of the clock comes along, those values are then allowed to propagate forward. So the 3 and the 2 are getting summed up to produce a 5. Then the clock comes along, and the 5 and the 3 propagate forward. And then 5 plus 3 equals 8. And again, we allow that to propagate forward. So resulting from this circuit, we'll see a waveform that looks something like what I've depicted below, what I've captured below in a screenshot. So this number that we're computing on, well, it's going to start off, assuming that it starts off with 1s, it's going to then produce a value of 2, and then 3, 5, and 8, and so on. Now, what's missing here, as I said, every sequential circuit needs reset. And reset is missing, which means in the circuit as I've drawn it here, we have no way to get this circuit into a known state to start off our sequence. We want our sequence to start off with 1 values, so we're going to use reset to inject 1 values into this circuit. And we can just inject a 1 at the front of the circuit and let the clock propagate that 1 forward. So as long as we're asserting reset, we're not using the summation. We're just providing a 1 value and allowing that 1 to propagate through our flops. So this is the circuit with reset, and we can express it in TL-Verilog as shown here. So we have our logic expression in TL-Verilog. If reset, then 1. Otherwise, the sum of the number and the previous number. And you'll notice this new notation here for previous and previous. Okay, so now that you've seen the Fibonacci series circuit, I'm going to let you guys try coding up a similar circuit on your own. This is just a slightly simpler variation of the Fibonacci circuit using a very common pattern. So I've left the Fibonacci series circuit here for your reference on the right, and using that as reference for the syntax, I'm going to ask you to code up a free-running counter. So this counter circuit is simply starting off with a value of 0, and every successive cycle is going to increment that count. So looking at the circuit, we have a count, and every cycle, that count is going to be added with 1. All right, so I'll give you guys time to try that on your own inside MakerChip. If you need to get back to a fresh MakerChip template, you can either just start up MakerChip again, or you can also look in the examples under the tutorials menu. There's an example there that's just the starting template. You can select that and click the button, and that'll load the to your editor. But make sure you've saved off your, again, your calculator, so you can return to that later, and you've bookmarked it. All right, so you can pause the video and try out the adder circuit.